A quiet stretch of mountains, long associated with stability, has begun to register movement again, and the pattern raises a set of measured but important questions. How often do these deeper shifts occur beneath one of the oldest mountain belts on Earth? What exactly is moving when tremors ripple through terrain formed hundreds of millions of years ago? And when a region far removed from active plate boundaries produces noticeable shaking, what does that reveal about the forces still at work beneath eastern North America? Recent seismic activity in the Appalachian Mountains has drawn renewed attention to the structural behavior of the continental interior. In 2025, a magnitude 4.1 earthquake occurred in eastern Tennessee, originating roughly 15 miles, or about 24 kilometers, beneath the surface. The epicenter was located southeast of Greenback, Tennessee, positioned within a region bounded by familiar geographic markers, including Gatlinburg to the north, Fontana Lake and Fontana Dam to the south, Cades Cove to the west, Knoxville near the northern edge, and Asheville just beyond the eastern boundary. Earthquakes in this region are not uncommon, but they are typically small in magnitude and often go unnoticed. A magnitude 4.1 event, however, is large enough to be felt across a wider area, particularly in communities built on sediment-filled valleys that can amplify ground motion. Reports from across eastern Tennessee indicated brief but distinct shaking, consistent with the depth and character of the seismic source. Unlike shallow earthquakes that rupture closer to the surface, this event originated deep within the Earth's crust, well below the layered sedimentary rocks that define the visible landscape of the southern Appalachians. The depth of the earthquake places it within what geologists refer to as the basement, a term used to describe the older crystalline rocks that lie beneath the sedimentary layers. These basement rocks form the structural foundation of the continent and extend to depths of many miles or several tens of kilometers. In this case, the seismic activity occurred approximately 12 to 15 miles, or 20 to 25 kilometers below the surface, indicating that the movement was not directly associated with surface faults or recent geological formations. Instead, the earthquake resulted from strike-slip motion along a fault embedded within this deep crustal layer. Strike-slip faults are characterized by horizontal movement, where blocks of rock slide past one another rather than moving vertically. This type of motion is commonly associated with plate boundaries, such as the San Andreas Fault, but it can also occur within continental interiors where ancient zones of weakness persist. In the case of eastern Tennessee, the fault responsible for the 2025 earthquake is oriented roughly east to west, reflecting a stress regime that differs from the more widely known transform systems along active plate margins. The presence of such stress within the interior of the North American continent is linked to broader tectonic forces. Although the region lies far from active plate boundaries, it is still subject to compressional forces resulting from interactions along the edges of the continent. These forces are transmitted across vast distances, gradually accumulating stress within the crust. Over time, this stress can be released along pre-existing faults, many of which date back hundreds of millions of years to the formation of the Appalachian Mountains themselves. The Great Smoky Mountains, a prominent sub-range of the Appalachians, provide a clear example of the region's complex geological history. Rising sharply from the Tennessee Valley, these mountains exhibit significant topographic relief, particularly between Gatlinburg and Mount LeConte, where elevation differences reach approximately 1.6 kilometers, or about 5,200 feet. The rocks that compose these mountains are primarily sedimentary in origin, layered and folded through a series of ancient tectonic events that culminated in the assembly of the supercontinent Pangaea. These sedimentary layers are arranged in a shingled structure, having been thrust westward over one another during periods of intense compression. Beneath them lies the basement, composed of older metamorphic and igneous rocks that predate the mountain-building processes visible at the surface. The distinction between these layers is critical in understanding modern seismicity. While the surface rocks record the dramatic tectonic history of the region, they are not the primary source of current earthquake activity. Instead, it is the deeper basement rocks, largely hidden from view, that continue to respond to present-day stress conditions. The earthquake in 2025 did not involve the upward movement of rock that would contribute to mountain building or elevation change. There was no evidence of thrust faulting or vertical displacement that might alter the landscape. Instead, the horizontal slipping motion at depth produced seismic waves that traveled upward through the crust, eventually reaching the surface as ground shaking. This distinction is important because it highlights the difference between the processes that form the Appalachians and those that are currently active beneath them. The region in question is part of the East Tennessee seismic zone, one of the most active seismic areas in the eastern United States. Unlike the well-defined fault lines of the western United States, seismic zones in the east are often diffuse, consisting of networks of small faults distributed over a broad area. Earthquakes within this zone are typically low in magnitude, often ranging between magnitude 2 and magnitude 3, and are detected primarily by sensitive instruments rather than by human observation. However, the occurrence of a magnitude 4.1 event falls outside the most common range and therefore attracts greater attention. Historical records indicate that the region has experienced larger earthquakes in the distant past, though such events are rare on human timescales. Geological evidence suggests that some of these larger events may have occurred tens of thousands, or even hundreds of thousands, of years ago, leaving subtle traces in the landscape that are difficult to detect without detailed study. One factor that may influence seismic activity in this region is the long-term evolution of the Earth's crust following the last glacial period. During the peak of glaciation, large ice sheets covered much of North America, exerting significant weight on the crust. Although the Appalachian region was not directly covered by the thickest ice, it was still affected by the redistribution of mass across the continent. As the ice sheets melted and retreated, the crust began to adjust, a process known as isostatic rebound. This adjustment can alter stress patterns within the crust, potentially reactivating old faults or creating new zones of weakness. In addition to glacial effects, ongoing erosion continues to shape the Appalachian landscape. Rivers and weathering processes gradually remove material from the mountains, reducing the load on the crust. While this process occurs over extremely long timescales, it can contribute to changes in stress distribution, particularly in regions where the crust is already close to failure along existing faults. The interplay between erosion, isostatic adjustment, and tectonic stress creates a dynamic system in which even ancient mountain ranges can exhibit measurable seismic activity. The characteristics of seismic wave propagation in the eastern United States also play a role in how earthquakes are experienced. The crust in this region is older and more rigid compared to the western United States, allowing seismic waves to travel greater distances with less attenuation. As a result, an earthquake of moderate magnitude can be felt over a much larger area. In the case of the 2025 event, shaking was reported across multiple counties, even though the epicenter was located deep beneath a relatively localized area. Instrumentation across the region has recorded numerous smaller tremors both before and after the magnitude 4.1 event, suggesting a pattern of ongoing microseismic activity. These smaller events, often below magnitude 2, are not typically felt, but provide valuable data on the behavior of faults at depth. By analyzing the frequency, distribution, and characteristics of these tremors, researchers can gain insight into the stress state of the crust and the potential for future activity. Despite the presence of these tremors, there is no clear indication that they are building toward a significantly larger event. The release of stress through small earthquakes can, in some cases, reduce the likelihood of larger ruptures by preventing the accumulation of strain. However, the relationship between small and large earthquakes is complex, and the absence of large events in recent history does not necessarily preclude their occurrence in the future. The geological setting of the Appalachian region further complicates the interpretation of seismic data. The crust here is heterogeneous, consisting of rocks with varying compositions, strengths, and histories. Faults within the basement may not have clear surface expressions, making them difficult to map and study. In many cases, their existence is inferred primarily from seismic activity rather than direct observation. This lack of visibility adds a degree of uncertainty to assessments of seismic hazard. At the same time, the relatively low level of seismic activity compared to active plate boundary regions means that the overall risk remains limited. Buildings and infrastructure in the eastern United States are generally not designed to the same seismic standards as those in more active regions, but the infrequency of strong earthquakes has historically justified this approach. Events like the magnitude 4.1 earthquake serve as reminders that seismic risk, while low, is not absent. The broader context of eastern North America includes several other seismic zones, each with its own characteristics and history. The East Tennessee seismic zone is one of several areas where the crust appears to be particularly responsive to stress. Others include regions in the central United States, where past earthquakes have demonstrated the potential for significant ground shaking despite the absence of nearby plate boundaries. Together, these zones illustrate that the interior of the continent is not entirely stable, but rather contains a network of inherited structures that can be reactivated under the right conditions. As monitoring continues, attention remains focused on the patterns emerging from recent activity. The distribution of tremors, their depths, and their mechanisms all contribute to a growing data set that can be used to refine models of crustal behavior. Each new event, whether felt or not, adds another piece to the broader understanding of how stress is accommodated within the Earth's interior, in regions far removed from the edges of tectonic plates. Monitoring networks across the Appalachian Mountains continue to register subtle but persistent activity following the magnitude 4.1 earthquake in eastern Tennessee, and the pattern that emerges from these recordings provides a clearer view of how stress is distributed beneath this long, stable region. Seismographs positioned across Tennessee and neighboring states have captured clusters of microtremors occurring at similar depths, generally between 12 and 16 miles, or about 20 to 26 kilometers below the surface. These small events, often too weak to be felt, are not random. They tend to align along narrow zones, suggesting the presence of fault structures that remain active at depth even if they are not visible at the surface. The behavior of these faults reflects a broader stress regime affecting eastern North America. The continental plate is being compressed along a northeast to southwest axis, a slow but continuous process driven by interactions along distant plate boundaries. This compression does not produce dramatic surface deformation in the Appalachians, but it does accumulate energy within the crust. Over time, that energy is released in the form of earthquakes, when stress exceeds the strength of rocks along pre-existing weaknesses. In eastern Tennessee, those weaknesses are largely confined to the basement rocks. Unlike the layered sedimentary formations that dominate the surface, the basement consists of older, more rigid material that has undergone multiple cycles of deformation over hundreds of millions of years. These rocks contain fractures and faults that formed during ancient tectonic events, including the collisions that built the Appalachian Range. Although these structures have long since ceased to shape the landscape directly, they remain zones where stress can be concentrated and released. The magnitude 4.1 earthquake demonstrated how energy stored at depth can travel efficiently through the crust. Because the rocks of the eastern United States are relatively dense and continuous, seismic waves lose less energy as they move outward from the source. This allows shaking to be felt over a wider area than would be expected for a similar magnitude event in regions with more fragmented or younger crust. In the case of the 2025 event, shaking was reported not only near the epicenter southeast of Greenback, but also in surrounding communities extending toward Knoxville and beyond. Geographic features across the region influence how that shaking is experienced. Valleys filled with sediment can amplify ground motion, while solid bedrock tends to transmit waves more directly. In areas near Gatlinburg and the foothills of the Great Smoky Mountains, variations in local geology can lead to differences in intensity even over short distances. These variations are consistent with observations from past earthquakes in the region and highlight the importance of local conditions in determining the impact of seismic events. The absence of surface rupture in the 2025 earthquake is also consistent with its depth and mechanism. Strike-slip motion occurring more than 10 miles or 16 kilometers underground does not typically produce visible displacement at the surface. Instead, the movement is confined to deeper layers, and its effects are transmitted upward as waves rather than as direct structural changes. This distinction helps explain why the landscape of the Appalachians remains largely unchanged, despite ongoing seismic activity. Long-term records suggest that the East Tennessee seismic zone has maintained a relatively steady level of activity over time. While the frequency of small earthquakes fluctuates, there is no clear trend indicating a sustained increase or decrease in seismicity. The occurrence of occasional moderate events, such as the magnitude 4.1 earthquake, fits within this broader pattern. These events are infrequent but not unprecedented, and they provide valuable data for understanding the limits of stress accumulation in the region. Geological evidence points to the possibility of larger earthquakes in the distant past. Studies of ancient sediment disturbances, landslide deposits, and subtle fault scarps indicate that stronger shaking has occurred, though likely separated by intervals of tens of thousands of years or more. The lack of recent large events does not eliminate the possibility, but it does suggest that the recurrence interval for such earthquakes is very long compared to human timescales. One factor that continues to be examined is the role of crustal loading and unloading in influencing stress. During the last glacial maximum, large ice sheets covered much of northern North America, altering the distribution of weight across the continent. Although the southern Appalachians were not directly buried under thick ice, they were affected by the shifting balance of mass. As the ice melted, the crust began to adjust, a process that continues at a slow rate even today. This adjustment can modify stress fields and potentially contribute to the reactivation of faults. Erosion also plays a role, though its effects are gradual. The Appalachian Mountains have been worn down over millions of years, reducing their elevation and redistributing material into surrounding basins. This removal of mass changes the pressure on the crust, allowing it to respond by rising slightly or by redistributing stress internally. While these changes occur over very long periods, they are part of the overall system that governs how and where earthquakes occur. Another aspect of the region's seismic behavior involves the orientation of faults relative to the current stress field. Not all faults are equally likely to be reactivated. Those that are aligned in a way that allows them to accommodate the present direction of compression are more prone to movement. In eastern Tennessee, the east-to-west orientation of certain basement faults makes them suitable for strike-slip motion under northeast to southwest compression. This alignment helps explain why earthquakes occur along specific lines rather than being distributed evenly throughout the crust. Advances in seismic monitoring have improved the ability to detect and analyze small earthquakes in the region. Modern instruments can record events with magnitudes well below 1, providing a detailed picture of how stress is released over time. By examining the timing and location of these micro-events, it is possible to identify patterns that might not be apparent from larger earthquakes alone. These patterns can reveal whether stress is being released gradually or whether it is accumulating in ways that could lead to larger events. Despite these advances, there are limits to what can be predicted. Earthquake occurrence depends on a complex interplay of factors including rock strength, fault geometry, and fluid pressure within the crust. Small changes in any of these variables can influence when and where an earthquake will occur. As a result, while it is possible to assess general levels of risk, it remains difficult to forecast specific events with precision. Infrastructure across the region reflects the historically low level of seismic hazard. Buildings, roads, and dams have not typically been designed with strong earthquakes in mind, particularly in rural and mountainous areas. However, the ability of seismic waves to travel long distances in the eastern United States means that even moderate earthquakes can have a wider footprint. This has implications for planning and preparedness, especially in areas with older structures. The presence of major features such as Fontana Dam adds another layer of consideration. Large dams are engineered to withstand a range of stresses, including seismic forces, but ongoing monitoring is essential to ensure their continued stability. Data from regional earthquakes contribute to assessments of how these structures respond to ground motion and whether any adjustments are needed over time. For viewers following developments like this, staying informed is key. If you found this breakdown helpful, make sure to like, share, and subscribe, and tap that hype icon to help this reach a wider audience so more people can stay aware of what is happening beneath the surface.